What is a monatomic element? In a monatomic element, it exists as one single atom. It does not bond. And this is because it achieves stability by having a full stable outer electron shell. An example of this is helium, but all of the noble gases we know have achieved a full stable outer electron shell. These only contain something called London dispersion forces, which are classified as intermolecular forces, which we'll go into in a wee bit more detail later. What is a covalent bond? So let's recap from National 5. In a covalent bond, atoms share pairs of electrons. And the definition of a covalent bond is that a covalent bond is the result of the two positive nuclei being held together by their common attraction of the shared pair of electrons. And what we can see here in this diagram, where there's the overlap of the molecular orbitals, we have a covalent bond. That's where the shared pair of electrons can be found. So we're going to be looking at the different classifications of covalent bonds. The first one we're looking at is non-polar covalent bonds. Non-polar covalent bonds are formed when the attraction of the atoms for the pair of bonding electrons is the same. So what we can see for the diatomic elements, which are elements which are made up of two atoms of the same element, they will have the same electronegativity value. So if we look at hydrogen, each hydrogen atom has a pull of 2.2, so therefore the electrons will be shared equally within the bond. These only contain London dispersion forces, LDFs, and you have to know which elements in the periodic table only contain LDFs. So these are your 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine, and 2 special elements which we'll learn this year, which is sulfur, which has the molecular formula S8, and phosphorus P4. So what actually are London dispersion forces? Well, these are the forces which can be found between atoms. They're known as intermolecular forces. The negative electrons which orbit the positive nucleus, the distribution of the negative electrons temporarily change due to the path of orbit, which is different for each electron shell. These temporary induced dipoles are created. So London dispersion forces are forces of attraction that can operate between all atoms and molecules. When the electrons are found more densely on one side of the atom, we annotate that as delta negative, and if they are less densely populated on that side of the atom, we would call that delta positive. So what is the definition of London dispersion forces? They are formed as a result of the electrostatic attraction between temporary dipoles and induced dipoles caused by the movement of electrons in atoms and molecules. So let's look at monatomic elements and compare the strength of the LDFs. The more electrons an atom or molecule has, the stronger the LDFs. So let's compare helium and neon. Here we've drawn the electron arrangement diagrams to give us a pictorial version and make it a wee bit easier for us to see what's happening. We know that they're monatomic and exist as single atoms, therefore will not have any bonds, but do have the London dispersion forces, which are the attraction between atoms, single atoms that exist. We can see from the diagrams, however, that helium only has 2 electrons times 1 atom, and therefore has a total of 2 electrons, whereas neon has 10 electrons per single atom and has a total of 10 electrons. Because neon has more electrons, it's going to have more London dispersion forces, therefore more energy required to break these, so therefore it will have a higher boiling point. Let's compare the LDFs, the strength of the intermolecular forces of diatomic elements. So the question asks, oxygen and fluorine are both gases at room temperature. Explain fully in terms of the structure and bonding which has the higher boiling point. So if we look at oxygen, oxygen has a double bond between the atoms and fluorine has a single bond between the atoms. Firstly, we can see that there are 2 single atoms, so we're going to have to look up the electronegativity of those. So oxygen has 3.4, oxygen has 3.4. Because there's no difference in electronegativity, this would be classed as non-polar. Non-polar only has LDFs. Fluorine, the electronegativity of that is 4. The other fluorine is also going to be 4. Again, no difference in electronegativity, so it's going to be non-polar with LDFs. So to compare the strength of the LDFs, we need to quantify the number of electrons. Each oxygen atom has 8 electrons times the 2 atoms, which will give us a total of 16 electrons. For fluorine, each atom has 9 electrons times the 2 atoms which are found in the diatomic element, which will give us a total of 18 electrons. And because fluorine has more electrons, it has more LDFs, therefore more energy required to break these, so a higher boiling point. So let's compare a diatomic element to a monatomic element. Chlorine and neon are both gases at room temperature. Explain fully in terms of the structure and bonding which has the higher boiling point. So you can pause the video and have a go at this, and once you've written down your answer, you can compare it to my worked example. So chlorine is a diatomic element, so therefore we look up the electronegativity. It's 3.2. The other chlorine atom's also going to be 3.2, so there's no difference in electronegativity, which means that chlorine is going to be non-polar. It will only contain London dispersive forces. Neon is a noble gas. It's found in group 8 or 0 of the periodic table, so therefore it's going to be a single atom, so therefore monatomic, and will also only have LDFs. At this point we have to quantify the electrons. So for chlorine, it's got 17 electrons times 2 atoms as it's diatomic, which gives us a total of 34 electrons. Neon has 10 electrons per single atom, which gives us a total of 10 electrons. So therefore, as chlorine is diatomic and has more electrons, it's going to have more LDFs, therefore more energy required to break these, so therefore a higher boiling point. This past paper questions from the Higher 2017, written 1C. The boiling point of chlorine is much higher than that of argon. Explain fully in terms of structure and the type of van der Waals forces, that's intermolecular forces, present, why the boiling point of chlorine is higher than that of argon. So we write down the structure for chlorine, which is diatomic. We look up the electronegativity, which is 3.2. There's no difference in electronegativity, so it's classed as non-polar and will only have LDFs. Argon is a group 0 or group 8 element. It's a noble gas. It exists as a single atom, so would be monatomic, and again would only have LDFs. We have to quantify the electrons. Chlorine has 17 electrons times 2 atoms, which is 34 electrons. Argon has 18 electrons times 1 atom, which gives us 18 electrons. And because chlorine is diatomic, it has more electrons, therefore more LDFs, and will then require more energy to break these, so a higher boiling point. This past paper questions from the Higher 2015, written 1B part 3. The melting point of sulphur is much higher than that of phosphorus. Explain fully in terms of the structures of sulphur and phosphorus molecules and the intermolecular forces between the molecules of each element why the melting point of sulphur is much higher than that of phosphorus. So we have to know the formulas for sulphur and phosphorus, which is S8 and P4. Because it's all just sulphur atoms, there's going to be no difference in electronegativity, so it's going to be classed as non-polar and have LDFs. Similarly, the phosphorus is all just phosphorus atoms, so there's going to be no difference in electronegativity, so will be classified as non-polar and only have LDFs. We then have to quantify the electrons. So for the sulphur, each sulphur atom has 16 electrons times the 8 atoms, which is found in the molecular formula, which will give us a total of 128 electrons. Phosphorus, each phosphorus atom has 15 electrons times 4 atoms, which gives us a total of 60 electrons. So because sulphur has more electrons, it will have more LDFs, therefore more energy is required to break these, so therefore the higher boiling point.